Unfortunately, next week is a holiday, right? Is it holiday or not? Holiday? If you like to have a class, we can have. 수업 일이 공휴일. 한글날이 공휴일이에요, 아니에요? 공휴일이에요? 그럼 수업 안 하는 게 맞나? Okay. So no. October 9th, we don't have a class. And second quiz on October 23. So it will be 2.5 hours and no class. I think it will be 2 hours, but no class. I have to attend the meeting. 23, so it's a 2 hours quiz. Maybe 2.5, between 2.5, and no class. I don't know what is that. So it will be 14 to 16:30. So it will be a little over 2 hours. So I guess you can prepare up to 3 pages of cheating sheet. And quiz is from whatever from the last one to whatever we are learning on the previous week of that quiz date. So it's mostly complex variables. So we found that the complex number z is x plus iy satisfies the 4 basic arithmetic operations, so can be used to define the function. So before we do that, we have a different representation of complex numbers. So complex numbers actually can be represented by the point in 2-dimensional space. So distance from the origin to the point z is denoted by r, and angle with the x-axis is defined as theta. So z maybe use a different notation for point. So I will say P can be represented by a point P, xy in xy plane. And characterized by two parameters, x and y, or r two parameters, r and theta. R is given by x squared plus y squared. Theta is arctangent y over x. So this is x, this is y. Then z is x plus iy can be written as r cosine theta, I r sine theta, r to the cosine theta plus I sine theta. So this representation of a the complex number z by r and theta is called polar representation. It has a name, polar representation. And first used by the French mathematician René Descartes in 18th century. The polar representation has a unique property that actually the product of two complex numbers can be written as addition of angle and the multiplication of the radius. So you see that if the 2 point P1, x1, y1, P2, x2, y2. So this is theta 1, r1. This is theta 2, r2. Then z1 is r1 cosine theta 1, I sine theta 1. z2 is r2 cosine theta 2 plus I sine theta 2. So if we multiply them together, what happens? Then z1, z2 is r1 cosine theta 1 plus I sine theta 1, r2 cosine theta 2 plus I sine theta 2 is r1, r2, and let's multiply them together. So it's cosine theta 1, cosine theta 2, right? If we multiply the imaginary part together, what do we get? Minus I sine, no, not I, sorry, sine theta 1, sine theta 2, and imaginary part is sine theta 1, cosine theta 2, theta 1. Somebody can turn on the air conditioner. It's a bit warm. Is it turned on already? Okay. Let's set the temperature a little bit lower. So this sine theta 1, cosine theta 2. and cosine theta 1, sine theta 2. And this may be familiar to you. Anybody still remembers addition theory, 합법 정리? So this is cosine theta 1 plus theta 2, right? I mean, if you trace back to your high school days, you probably have studied this, especially it's well summarized in 수학의 정석, right? So when I was a high school student, I used the 수학의 정석 as a reference book. Is it still around? And another reference book was 해법 수학. So I used basically two books. I don't know. Probably 해법 수학 may not be around anymore. But 수학의 정석 is still there, right? This is sine theta 1 plus theta 2. So R1, R2 cosine theta 1 plus theta 2 I sine theta 1 plus theta 2. So when you multiply two complex numbers, you can represent in polar representation that it's a product of magnitude or distance, R1, R2, and addition of two angles, theta 1, theta 2. So we can do many things. So we can continue this. R cosine theta plus I sine theta. So z square can be r square cosine 2 theta I sine 2 theta, right? Z to the cube is r to the cube cosine 2 theta 3 theta I sine 3 theta, right? We could just add the angles to keep continuing. And z to the n is r to the n cosine n theta plus I sine n theta. So this is a very interesting result. And especially, let's set r equal to 1 for now. Then z is simply cosine theta plus I sine theta. Let's say this is f theta. And z to the n is cosine n theta I sine n theta is basically f theta to the n, and also same as f n theta. Very interesting function, right? So so there is a function that if you take power of n, the same as you just change the argument by n. So anybody knows that kind of function that has this property? Exponential function? Right? So f must be exponential function. Must be an exponential function, right? So we can say f theta is exponential alpha theta. So we are using a lot of Greek letters this semester. And I'm going to show that alpha is I. I will show. You can show soon in the next page. Am I going too slow? Because we are facing another quiz in 2 weeks, so I'm trying to go as slow as possible. If you think I'm going too slow, just let me know. I can go a little faster. So f theta cosine theta plus I sine theta is exponential alpha theta. So let's use a Taylor expansion. Probably you have studied Taylor series in your freshman calculus, right? So exponential alpha theta is 1 plus alpha theta plus alpha zeros squared over 2 plus 3 factorial alpha cube theta cube 4 factorial alpha fourth theta fourth, etc., right? I mean, if you can check the freshman calculus book for that. And anybody remembers the Taylor series for cosine theta? 1 minus theta square over 2, right? Plus 4 factorial theta to the fourth minus blah, blah, blah. Sine theta is theta cube over 3 factorial plus, right? So you can just compare term by term. Then 1 plus alpha theta plus 2 factorial alpha square theta square plus 3 factorial alpha cube theta cube plus 4 factorial alpha fourth theta fourth must be same as 1 minus theta square over 2 plus 4 factorial theta to the cube blah 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 plus I. This is theta, right? 1. Oh, sorry, I was confused. 1. So theta minus theta cube over 3 factorial, blah, blah, blah. So we can compare. So this term must be same as this, right? So alpha theta is I theta. And this must be same as this, right? Alpha square theta square over 2 factorial is minus 2 factorial over theta square, etc., etc. So what do we have? Alpha is I. So we have a very strange representation of exponential function that this is page 2, page 3. So we have exponential I theta is same as cosine theta plus I sine theta. It has a name. It's called Euler's formula. So exponential of I theta is same as cosine theta plus I sine theta. And this Euler's formula is a very interesting property. So can I move on? Euler's formula. Exponential I theta is cosine theta plus I sine theta. Electromagnetic wave of course is solution of Maxwell's equation. Has the form exponential I k c minus omega t. So this is cosine kz minus omega t plus I sine kz minus omega t. So assuming that when t is 0, then this function has a cosine kz plus I sine kz form, right? So if we take a real part, then this is c-axis, starting with something like that. When kz minus omega t is 2 pi, what happens? So this point, when z is equal to 0, this is z is equal to 0. But when same z must be k over 2 pi plus omega t. Sometime later, then same pattern appears. This is z-axis. This is z is k over 2 pi plus omega t. For t is 0. That means the shape of function is propagating in z-axis with the t, right? So that means shape of a function in z propagate along z-axis when with increasing t. Tx. So as time goes by, the same functional form is propagating into positive z-axis, right? So that means the light wave is a propagating solution. Or electromagnetic wave. And because of the solution is given by Euler's formula. So we know that if I call somebody, then my voice will transform carried by the electromagnetic wave, right, microwave. So you can call somebody in the distance. And speed of propagation is, of course, very fast, speed of light. So wave is propagating because it's Euler's formula. So Euler's formula actually allows this, the propagation of electromagnetic wave. Or this particular form of a solution is given by this Euler's formula. So this is really amazing. This Euler's formula, representation of exponential I theta by cosine theta plus I sine theta, is actually given by this space-time structure of this universe. I mean, if you have a different universe, then the Euler's formula will have a different form. Then they might have a solution of Maxwell's equation which may not propagate. But because this space-time structure of this universe allows the Euler's formula given by this form, and it allows the propagating solution. I'm not very religious man, but according to the Bible, that the first sentence was there was a light in the beginning, right? I mean, 태초에 빛이 있었다. But I think the more exact sentence should be there was a Euler's formula in the beginning. So 태초에 Euler의 공식이 있었다. So I think there should be more exact formulation of the meaning of that first sentence. But I'm not going to write down because it might contradict some of the belief of the religion by some students. So, but that's my belief, that in the beginning of this universe there was a Euler's formula that allows the light propagating solution. If the space-time structure is different, then the Euler's formula might have different form, which may not be a propagating solution. So where were we? It's Euler's formula, right? Before I proceed, today seems to be the attendance rate is quite low. So can you lock the door? 뒤에 문 잠그세요. So before I proceed, it's a good chance to have a surprise quiz. The first surprise quiz. So just to have any paper. So on the paper, your serial number and name. So question number, I'm going to have only one question, one. What is your name? And it'll be 10 points. And 3 minutes is okay? Your name, not my name. Just grab a piece of paper. Just write your name. Question number 1. And you will get 10 points. So surprise quiz is actually the substitute for 출석책. So it's all or nothing. I mean, if you happen to be here, then you will get 10 points. If you're not, then you will get 0. So anybody need more time? Raise your hand. All done? Yeah, let's collect it from the back. So you have to write your name twice. On the top and the answer sheet. Okay? So question number 1, what is your name? Actually, I was expecting that the attendance rate would be low. Today is, tomorrow is holiday. And starting a holiday with the long weekend. Some students might have taken the liberty of taking some trip or other things. All right. Anybody who haven't submit the answering sheet? Okay. So we can now open the door and continue the. So where were we? So Euler's formula gives a very interesting result. What if expansion minus I theta is expansion theta minus I minus theta, right? The same as. So you can write cosine minus theta plus I sine minus theta. So cosine minus theta is same as cosine theta, but sine minus theta is minus sine theta, so minus I sine theta. So we can combine them together, exponential I theta plus exponential minus I theta is 2 cosine theta, right? So cosine theta, I minus I cancel each other. So we have cosine theta is 2 over exponential I theta. So that's probably the definition of cosine theta as well. If we subtract them together, what happens? Exponential I theta minus exponential minus I theta is 2I sine theta. Sine theta can be written as 2I exponential I theta minus exponential minus I theta. Not very difficult. So there is another way, cosine theta 2 over exponential I theta plus exponential minus I theta. Sine theta is 2I exponential I theta minus I theta. So far, so good. Not very difficult, right? Right. So let's just summarize again. Euler's formula is cosine theta, I sine theta. Cosine theta can be exponential I theta over 2. Sine theta 2 over I theta. I think what if theta, and you assume that this relation is valid, for general theta can be complex numbers too. We can assume that this relation is valid for any theta, including complex numbers. So set theta is I zeta. So zeta. Then cosine I zeta is exponential I zeta, exponential minus I zeta, 2 over exponential minus zeta. I is minus, and minus I is plus. And it is a familiar type of function, right? Cosine hyperbolic theta. And sine I zeta is 2I exponential I zeta minus exponential minus I zeta is 2I exponential minus zeta minus zeta. So it's same as minus I over 1 2 exponential zeta minus zeta. So maybe we need some space here. So if we can move this is minus 1 over I. And what is exponential zeta minus exponential minus zeta over 2? Sine hyperbolic zeta. And 1 over minus I is actually same as I. So we have cosine I zeta is same as cosine hyperbolic zeta. Sine I zeta is same as I sine hyperbolic zeta. So it is convenient if you know some Greek alphabet. Alpha, beta, gamma, delta, epsilon, etc. Iota, zeta, lambda, kappa, mu, nu, sigma, tau, theta, pi, rho, psi, zeta, eta, zeta, we have that. How many? 24, there must be. I'm phi, psi, what else? Omega? One, two, three, four, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20, 21. We have three more. Omicron, gamma, delta, H, theta, pi, phi, tau, kappa, etc., etc. I don't remember everything. So, how about cosine z? Of course, it's cosine x plus iy. So it is 2 over exponential iz exponential minus iz, right? According to the definition. 2 over exponential I x plus iy minus I x plus iy exponential ix minus y plus exponential minus ix plus y so 1/2 exponential minus y cosine x plus I sine x plus exponential y cosine x minus I sine x. So let's put them together. Cosine x one-half exponential y exponential minus y, right? Plus I sine x minus y minus exponential y. So this is cosine hyperbolic y, right? And this is minus sine hyperbolic y. So we have some space here. So this result can be put into cosine x cosine hyperbolic y minus I sine x sine hyperbolic y. But actually, if we use this is 2, 3. By the way, if we use x plus iy as a addition theorem, 합법 정리, cosine x, cosine iy minus sin x, sin iy, right? This is a addition theorem. Cosine addition theorem. Then cosine iy is cosine hyperbolic y, right? So cosine x, cosine hyperbolic y minus sin x, sin iy is I sin hyperbolic y. So this result and this result is same, right? It's comparable to each other. So you can use addition theorem of sine and cosine. And perhaps you can take a break for a few minutes before we continue. Was I going too fast? Okay. 네? 양호실 갔다 왔다는 거 뭐 있어요?
저기서 물어봤는데 종이 같은 거 약이나 이런 거 받았는데 그 정도는 아니에요.
그거 보여주고 그럼 해요. 왜?
퀴즈 봤을 때 제가 잠시 화장실에 갔거든요. 원래 옆에 앉아있고 근데 제가 뒤에 빨리 들어와서
화장실 가느라고 못 봤어요?
아니 내가 들어가서 다른 친구가 앉아있었는데
네.
안 온 줄 알고 원래 여기 앉아있다가 저 끝났는데
근데
그래서 퀴즈를 제 걸 써서 내줬는데 저는 이제 저 들어갔으니까 시험을 제가 봤죠. 근데 서로 이게 그래서 두 장이 제 이름으로 두 장이 제출이 돼가지고
뭐야? 서로 해준 거야?
그러니까 해달라는 말을 안 했는데 이제 그러니까 잠깐 나갔는데 화장실에
그러면 치팅이잖아. 이번만 봐줄게.
감사합니다.
이거 조교한테 보여주고 그러면 네.
앉아 있다가 잠깐 화장실 갔다 왔는데 사이에 그 있다가
오케이. 네. 네?
질문 하나.
네.
예전에 수업하신 거 중에
네.
저희가 이제 크로스를 BAC, CAB로 정의했잖아요.
네.
교수님 써주신 예제 중에 컬컬을 이런 식으로 써서 그러면 얘가 이거
이거는 저희 파티자님 때문에 쓸 수 있는 거죠?
예,
이렇게는.
근데
파티자니 아니면 이렇게 있어.
좌표계의 문제라고 있어요.
이렇게 쓸 수 있지 않나?
예.
이거는 쓸 수 있지. 이거 뭐야? 이 마이너스 이게 F였으면 이거 물어보는 건 아니에요?
아, 그 문제 말가 결과적으로 궁금한 게
이거는
델 벡터는 말이 안 되는 거잖아요.
델도 벡터죠.
그러니까 델 펑션이 아니라 델 벡터
벡터. 그게 벡터죠. 벡터인데 뒤에 함수가 와야지 적용되는 거죠. 벡터는 벡터인데
이게 이런 식으로 써버려지는 거예요.
그러니까 이렇게 써야죠. 내죠. 델 내죠.
이걸로 계산을 해도 되긴 하는 거죠.
그렇죠. 이 경우는 B니까 이렇게 되잖아. 그 다음에 C, A, B겠지, 그죠? 네네.
델 오퍼레이터는 항상 펑션에만 취할 수 있는 거죠.
그렇죠. 펑션에 작용하는 건데 벡터처럼 생각할 수 있는 거죠. 왜냐면 이게 그 축이 있잖아요. X축, Y축, Z축이 있으니까. 그러니까 벡터처럼 생각할 수 있는 건데 그냥 통상적인 벡터는 아니고 그 뒤에 항상 함수가 와줘야 되는 거죠. 잠깐. So I'm defining some functions, basic functions. So how about sine z? We just found out that this trigonometric function addition theorem works for complex functions as well. So I'm just going to use that. So sine x cosine iy cosine x sine iy. So for this step we use trigonometric function addition theorem. So 삼각함수 가법 정리 that we all learned in high school days. So sin x cosine hyperbolic y I cosine x sine hyperbolic y. Tangent z. Oh, it's a bit cosine z, sine z. Cosine x cosine hyperbolic y minus I sine x sine hyperbolic y. Sine x cosine hyperbolic y I cosine x sine hyperbolic y. Oh, looks a little bit complicated, right? So let's try to simplify. So easiest way of simplifying is just multiply by 1. So I'm going to multiply complex conjugate over denominator. Oops. So called denominator is 분모. Denominator is called 분자. 분모, 분자. So cosine x cosine hyperbolic y plus I sine x sine hyperbolic y, and you multiply the same thing. It's basically 1, right? Cosine x cosine hyperbolic y plus I sine x sine hyperbolic y. So it's called TZ, and you can write this way: dxy and xy. So let's calculate the denominator first. TZ is cosine x cosine hyperbolic y plus I sine x sine hyperbolic y. Cosine x cosine hyperbolic y, oh, this is minus, sorry, plus I sine x sine hyperbolic y. And you know how to calculate the multiplication of two complex function by its complex conjugate is cosine square x cosine hyperbolic square y, right? Sine x sine hyperbolic square y. Actually, it can be simplified a little bit. Same as, so I'm going to use this 1 minus cosine square x. Then what happens is cosine square x cosine hyperbolic square y minus sine hyperbolic square y plus sine hyperbolic square y. And we know this relationship. Cosine hyperbolic square y minus sine hyperbolic square y is equal to? You don't remember that? 1. Very good. You have to know this relation. So if we put this here, then denominator is simply cosine square x plus sine hyperbolic square y. Denominator I didn't do my homework to how to make a copy and paste in the next page, so I have to write it all terms together. I will try to do it next time. Sine, cosine, I. So denominator sine, cosine hyperbolic, cosine, sine hyperbolic. So cosine square x plus sine hyperbolic square y. So that's cosine square x plus sine hyperbolic y. Sine x cosine hyperbolic y plus I cosine x sine hyperbolic y times cosine x cosine hyperbolic y plus I sine x sine hyperbolic y. So sine x cosine x and cosine hyperbolic square minus sine x and the real part, this and this, sine x cosine x sine hyperbolic y plus I cosine square x sine hyperbolic y cosine hyperbolic y plus I sine square x cosine hyperbolic y sine hyperbolic y. Very interesting formula, right? So it turns out that it's sine x cosine hyperbolic square y minus sine hyperbolic square y plus I cosine square x plus sine square x sine hyperbolic y cosine hyperbolic y. And this is equal to 1. This is equal to 1. So actually it can be simplified considerably. Sine x cosine x plus I sine hyperbolic y cosine hyperbolic y. So we have tangent z is sine x cosine x plus I sine hyperbolic y cosine hyperbolic y, and I don't remember. So cosine square x plus square y. So that's our formula for tangent z. Secant z cosecant z cotangent z is easy, 1 over tangent z. So you can do it as homework. How about cosine hyperbolic z? So we are covering the exponential functions first. Make some copy. I might be going a little bit fast. So we can do the same way to define cosine hyperbolic z. Even before that. So cosine hyperbolic z, cosine hyperbolic x plus iy. We don't know how to represent this, so exponential z plus exponential minus z, right? That's definition of a cosine hyperbolic z. So we can do the same thing. Exponential x plus iy, exponential minus x minus iy. So 1/2 exponential x cosine y plus I sine y plus 1/2 exponential minus x cosine y minus I sine y. So 1/2 exponential x plus exponential minus x cosine y plus 1/2 I exponential x minus exponential minus x sine y is cosine hyperbolic x cosine y plus I sine hyperbolic x sine x sine y. Let's compare with the cosine z. Cosine z was, anybody remembers that? Cosine x, cosine hyperbolic y minus, right? I sine x sine hyperbolic y. So I'm not so sure if we can find the relationship here. Anyway, so this cosine hyperbolic z. It's a bit different compared. So I can ask you as homework to derive sine hyperbolic z, cotangent hyperbolic, no. Tangent hyperbolic z, secant hyperbolic z, CS hyperbolic z, cotangent hyperbolic z. Obtain the formula. And as always, my homework is for your good, so just do at home, or you don't need to give it to me. So we are going to have a long weekend, so that will give you time for spending some idle time with the homeworks, right? So we have covered the complex functions for especially trigonometric form and hyperbolic forms. And polynomials we can be also easily defined as we have a mosquitoes. For example, polynomial z square, z times z, x plus iy, x plus iy, x square minus I square plus I 2xy, right? Z cube, z square times z, x square minus y square plus I 2xy, x plus iy is, we are going to have 6 terms. The first one is easy, just x cube minus xy square plus I 2x square y plus I x square y minus I y cube minus 2 xy square. So x cube plus 3 x square y minus 3xy square minus y cube. I. And you can do blah blah blah. So homework. Try Z4, Z5, Z6, Z7, 4, maybe Z8. It's a test of your patience, right? Or persistency. Patience. Patient. Persistent. You have to be persistent. So far, single valued. That means one Z, you have one output Z. Single valued. But sometimes it is not. For example, Z1 to the half is a typical example of not single valued function. So before we do that, let's go back to the Euler's formula. Cosine theta plus I sine theta. Exponential I 0 is equal to, when theta is equal to 0, 1, right? Theta is equal to pi, we have minus 1, right? 2 pi, 1. 3 pi, minus 1. So we have exponential plus minus 2n pi, I is always plus 1. So z to the half is actually, you can have z times 1 to the half. And 1 can be exponential plus minus 2n pi I, right? So it is z times exponential plus minus 2n pi I, 1/2 is c half exponential plus minus I n pi. And this is actually very interesting. So when n is even number, then z half is fc is plus, right? But when n is odd, fc is minus c over half. So very tricky. So we have to worry about this argument too. So for that, it may be better represent in polar form. Pi, then we represent as a square root of z when theta is 0 to 2 pi. Then for general case, z to the 1/2 is plus root 2z minus root 2z. And theta is 2 pi otherwise. So for example, we can make a barrier in the xy plane called branch cut. And if there's a point above this x, and this is x exponential 2 pi I. So this is a barrier for the branch cut, and right above, just tiny distance from the x-axis called x. So above the x-axis, we can put z is equal to x. But below the x-axis, this point can be x times exponential 2 pi I, because you have to rotate 2 pi I, right? So this is a point above the x-axis. This is a point below the x-axis. Then z to the 1/2 is root 2x or minus root 2x, depending on where it is. So if you calculate fz here, then it's minus, right? Because you have 2 pi I. Maybe I should delete this. So using this definition, so using this knowledge, you can actually solve algebraic equations. Algebraic equation. For example, z squared is equal to 1. So 1 can be represented by many different ways, exponential, plus minus I 2 pi n, right? Then z is exponential plus minus I 2 pi n 1/2. So that is plus 1 minus 1, right? N is even, N is odd. Same way, c to the cube is equal to 1 can be solved using this, plus minus I 2 pi n. Then z is exponential plus minus 3 over I 2 pi n. So when n is equal to 0, z is simply 1, right? When n is equal to 1, what happens? Z is exponential 3 over I 2 pi. N is equal to 2. Z is exponential 3 over I 4 pi. So we can have a solution space here. And this is 2 pi over 3. This is 2 pi over 4. So exponential I 2 pi over 3 is cosine 2 pi over 3 plus I sine 2 pi over 3. So all sa tan cosine, right? So 2 pi over 3 is 120 degree. So cosine or sa 120 degree is minus 1/2. So minus 1/2 plus I square root of 3 over 2. And this one is minus 1/2 minus I square root of 3 over 2. The complex algebraic equation can be solved very easily using this notation. Another example of, I might going a little bit too fast, I think. The complex number function is easy up to single valued function, but the fractional power, then you have to think about a little bit more carefully. Another extreme case is a logarithmic function. So C R cosine C. C is x plus IY R exponential I theta, right? So you can represent, but actually you can multiply by 1, so this is R exponential I theta plus minus I 2 pi n. Same as this, I theta plus minus I 2 pi n. So log x or ln x ln z is ln r exponential I theta plus minus I 2 pi n. It's a very interesting expression. It's ln r plus I theta plus minus I 2 pi n, right? So this is multivalued function. And when theta is from 0 to 2 pi, we represent ln z as ln z. Big ln. We write this way. So again, we can put the branch cut here when you define the logarithm. So you don't want to see cross this space to make a single value. covered cosine trigonometric function, hyperbolic function, polynomial, and the fractional power function, like a z to the half, which is not single valued. So we consider both single valued function and multi-valued function. And what else do we need? Inverse function, cosine inverse. Right. So we are going to take a break after studying cosine inverse cosine function. Say W inverse C. Or cosine W is C, right? C is same as exponential IW, or square minus 2z exponential IW plus 1 is equal to 0. So this solution is written as z plus z squared minus 1 to the half, right? I put intentionally 1/2. Then IW is ln z plus z squared minus 1 to the half, or W is cosine inverse z is minus I ln c plus z squared minus 1 to the half. So obviously it is not single valued, right? Because it contains half term, and logarithmic function is not single valued. It's not single valued function. So homework can be derived sine inverse z, tangent inverse z, and likewise secant inverse z, cosecant inverse z, cotangent inverse z. And actually you can obtain the same thing for the cosine hyperbolic inverse z, sine hyperbolic inverse z, tangent hyperbolic inverse z, cosecant hyperbolic inverse. Maybe that's enough. Okay? Still is important. Secant inverse z, CS inverse z, cotangent hyper inverse z. So you can do this, derive these functions during the holiday too. I think I gave a good enough. And the best time to do the homework is when you when you have a blind date, 소개팅, but your partner didn't show up. So you are waiting for maybe 1 hour and then you go, right? If he or she doesn't show up in 1 hour, then you just go, right? Then the best way of spending time is doing your homework. 1 hour will be going very fast. So that's the time. So you can do homework on your blind date. On your blind date. Especially when you are studio, 바람 맞을 때. Maybe. So any questions? So I have enough homework and you have a long weekend, so maybe you have many chance to do blind date because you can do homework, right? Whatever. So basically we covered all the necessary complex functions so far, and if you don't have any questions, maybe we can take a break for maybe a few minutes before we continue. So with the definition of functions, next topic will be differentiation. So eventually we're interested in doing differentiation and integration. So of anybody remembers that the condition to obtain the derivative of real function? 연속, right? Continuous. The function needs to be continuous. So we obtain some region, it's called domain. We have C0. If continuous. Let's see equals C now. And when f is continuous, and finite, and domain D, the region is called the domain D. We can differentiate FC, but the derivative has to be unique. So we can So that's how we define the derivative, same as the real case. But you have to be really careful because, so say set fz u x y. So we can always represent the function with the real part. And imaginary part. And delta z is delta x plus I delta y. So there are two ways of approaching defining this derivative. First one, we set delta y is equal to 0 and allow delta x goes to 0. That's one way, right? So in this case, dz dfc is limit delta x goes to 0, delta x u x plus delta x y plus I v x plus delta x y minus u x y minus I v x y is basically partial x partial u plus I partial x partial v. Another possibility is we can set delta x equal to 0 and allows delta y goes to 0, right? Then in this case, delta y goes to 0 and delta z is I delta y, right? Because delta x here delta x, but here I delta y, and u x y plus delta y I v x y plus delta y minus u x y minus I v x y. But this is something like this: 1 over I partial y partial u plus partial y partial v, right? The same as partial y partial v minus I partial y partial u. So say this is 1 and this is 2. And we should have only one limit. So maybe we can have this space here. We should have only one limit, one derivative. It has to be unique. Means one unique derivative. That means 1 is equal to 2. Or that means partial x partial u is same as, so this has to be same as this, and this has to be same as this, right? So partial y partial v and partial x partial u v is minus partial y partial u. That's the condition for the derivative exist. And it is called, it has a name actually. It's called Cauchy-Riemann condition. Very important condition. And substantial portion of next quiz will be shown to show given function satisfies the Cauchy-Riemann condition, and then find the derivative. So, can I move on? This is a very simple condition, but really important condition in complex variables. Oh, I have done this wrong. So, FC is differentiable if partial x partial u is partial y partial v, and partial x partial v is minus partial y partial u, and the derivative dz df is very simply partial u partial x partial v. This is Cauchy-Riemann condition. And this is a very important property of a complex function to be able to whether it is differentiable or not. So let's start with a simple case. Check. Fz is z. X plus iy. Right? So u is x, v is y. So partial x, partial u is 1, right? Partial y, partial v is 1. So partial x, partial u is partial y, partial v. Partial x, partial v is 0. Partial y, partial u is 0, right? So 0 is 0. So partial x, partial v is minus partial y, partial u. So Cauchy-Riemann condition is satisfied. And dz df is partial x partial u plus I partial y partial v is equal to 1, right? So this function is differentiable. Can I move on? Another simple example. Fz is c square, x square minus y square plus I 2xy. This is probably the better example to show the Cauchy-Riemann condition. So uxy is x square minus y square, right? Vxy is 2xy. So partial x partial u is 2x. Partial y partial v is 2x, right? So partial x partial u is partial y partial v. Partial x partial v is 2y. Partial y partial u is minus 2y. So So partial y partial u is minus partial x partial v, right? So for this function, Cauchy-Riemann condition is satisfied, right? So we can define the derivative. So derivative dz df is defined by simply partial x partial u plus I partial x partial v is 2x plus I 2y is 2z. So z square is 2z. So you can actually differentiate like a real function. So you can differentiate complex function in the same way as the real function once they satisfy the Cauchy-Riemann condition. We can check the further properties. This is one way. So pulling, so I can, at this stage, I can give you some more homework, like z square, z cube. Can I move on? Okay, so this denominator part is homework. Fc c square d cube. Check for. Let me just write this way: Cauchy-Riemann condition, and find the dz df. So that can be a good homework. You can maybe 10 minutes. Let's try a little bit more complicated function. Cosine z. Anybody remembers the expression cosine x, cosine hyperbolic y, minus I, sine x, sine hyperbolic y, right? So uxy is cosine x, cosine hyperbolic y. Vxy is minus sine x, sine hyperbolic y. So partial x partial u minus sine x cosine hyperbolic y, right? And partial y partial u v is minus sine x. What happens if you differentiate sine hyperbolic y? Cosine. So they are the same, right? So if we compare with this, they are the same. So we have this relation. Partial x partial u is partial y partial v. How about partial y partial u is cosine x. And if we differentiate cosine hyperbolic y, you obtain sine. And partial x partial v is minus cosine x sine hyperbolic y, minus cosine x sine hyperbolic y. So again, partial x partial v is minus partial y partial u. So they satisfy the Cauchy-Riemann condition, right? So we can say that CR is satisfied. Then dz d cosine z partial x partial u plus I partial x partial v is minus sine x cosine hyperbolic y minus I cosine x sine hyperbolic y, which is same as minus sine z. So again, you can see that you can differentiate the function the same as the real function. And we call this differentiable complex function is analytic function. Differentiable and finite complex function is called analytic function. So when you say analytic function, it just means it's differentiable and finite. So up to now it's easy. I can do a little bit more complicated case. Can I move on? If I have an impression that I'm going to Z is Z complex conjugate. So U is X, V is minus Y. So partial X partial U is 1, partial Y partial V is minus 1. So this function is not differentiable. Sequent X, C. This is a little difficult part. 1 over cosine Z. Cosine X, cosine hyperbolic Y minus I sine hyperbolic X. It can be simplified. Remember that it's cosine square X. Too fast. So this will become cosine square X plus sine hyperbolic square Y, but cosine X cosine hyperbolic square Y plus I sine X sine hyperbolic square Y. So this is U X Y I V X Y. So U X Y cosine X cosine hyperbolic Y Vxy sine X sine hyperbolic Y cosine square X plus sine square Y. Let me try to, I don't know how I do that. I think I used to know. Let me try this. And Okay. Oh, I think I edit. Edit. Copy. And throw it away. Okay, let's try to see if I have. So edit, inspector, paste. Okay, so I can move. No, this is not. Maybe I should put this. Not this. Okay. Image from picture equation. Browser. Clipart. Clipart. Is this? No. I think it must be somewhere. Edit, paste. And can I move this? Can I move? No, it's not. Throw it away. It must be somewhere. Existing image clipart. I remember there was. Close. I don't know what to do. Sorry. I still haven't figured out. So it was a nice try, but it didn't work. So u cosine square x plus sine hyperbolic square y cosine x hyperbolic y, right? Let's free cosine square x plus sine hyperbolic square y sine x sine hyperbolic y. So let's take a partial derivative of x. It's not bad. You can do it. So you first differentiate the denominator. So it's minus sine x cosine hyperbolic y cosine square plus sine hyperbolic square y. And you differentiate the denominator. So we have cosine x cosine hyperbolic y. This is 1 over x if we differentiate minus, right? Cosine square x plus sine hyperbolic square y. And then you differentiate this with x. So 2 cosine x minus sine x. This part, if we differentiate the denominator, you first minus square, and then you differentiate this part again. So this is 2 cosine square x is 2 cosine x, and then minus sine x. You have to be really patient. So minus minus plus, we have cosine square x plus sine square y and square minus sine x cosine hyperbolic y cosine square x square y minus minus plus twice over cosine square x sine x and cosine hyperbolic y. Is that correct? 2, 2, 2, 2, 2. So. Yes. Cosine square x plus sine hyperbolic square y square. The first term. Oops. So sine x cosine square x. So the first term is minus sine x cosine square x cosine hyperbolic y minus sine x cosine hyperbolic y sine hyperbolic square y plus 2 cosine square x sine x cosine hyperbolic y. So this is sine cosine square x cosine hyperbolic y. We have 2 cosine square x sine x cosine hyperbolic square cosine hyperbolic y. So 2 become 1, right? So this cancels this. So we become cosine square x plus sine hyperbolic square y square. We have cosine square x sine x cosine hyperbolic y minus sine x cosine hyperbolic y sine hyperbolic y. Correct? Sine cosine square. That's this and sine x sine hyperbolic square. So cosine hyperbolic and sine x is common. Square, we have sine x cosine hyperbolic y cosine square x minus sine hyperbolic square y. That's partial x partial u. So we need 4 derivative and just 3 more, right? So partial y partial v. And next page. Signs. Okay. One, same, right? So 2 to go. Okay. Mistake. Denominator is the same. Sine, cosine. So use this. Maybe I can just copy this. Edit. Copy. Delete. Okay. So free cosine square x plus sine hyperbolic square y. This is sine x sine hyperbolic y, right? That's your free. So partial y partial v. The same way. So we first differentiate the denominator first. So sine x cosine hyperbolic y cosine square x plus sine hyperbolic square y, right? Plus sine x sine hyperbolic y. You have minus cosine square x plus sine hyperbolic square y square, and twice over sine hyperbolic y cosine hyperbolic y. So we can put them together. Square sine x cosine hyperbolic y cosine square x plus sine hyperbolic square y minus twice over sine x sine hyperbolic square y cosine hyperbolic square y is cosine square x plus sine hyperbolic square y square. We have a sine x cosine square x cosine square y plus sine x that's square, right? Cosine hyperbolic square y sine hyperbolic square y minus twice over sine x sine hyperbolic square y y. So x square y square. So which one will cancel each other? Which one? Second and third will cancel each other, right? So sine x cosine square x cosine hyperbolic y minus sine x cosine hyperbolic y sine hyperbolic square y. So we can combine them together as a cosine square x plus sine hyperbolic square y square sine x cosine hyperbolic y cosine square x minus sine hyperbolic square y. Okay, so what happens to the so we have shown this. Partial x partial u is partial y partial v. So how long does it take for me to do this? 10 minutes? 5 minutes? Now, voila. Just in case, I don't want. Partial y, no mistake. Difficult to remember. Maybe we need to do that. Okay. U cosine square x sine square y cosine x cosine hyperbolic y, right? Let me just double. So you first differentiate the denominator first. So we have cosine x sine hyperbolic y cosine square x plus sine hyperbolic square y plus denominator we have square, we have minus sign, and twice of sine hy and cosine hyperbolic y, right? So we put them together. cosine square x plus sine hyperbolic square y square, and okay, I'll just put it here. So we have this times this gives cosine cube, right? Cosine cube sine hx plus cosine x sine cube y minus twice over cosine x sine hyperbolic y cosine square y. We have to double check at this point. So I differentiate first by y. So cosine becomes sine, right? Sine hyperbolic. And I like to differentiate denominator. So denominator is same, but square minus 1 and twice over sine hyperbolic y and cosine hyperbolic y. So if we put them together, the first term is cosine cube sine hyperbolic y. Second term is cosine x sine hyperbolic cube y. And minus cosine x 2 sine hyperbolic y. Oh, it looks complicated. So let's divide by 1 each. What happens? The first term, cosine x sine hyperbolic y, we have cosine square x minus 1, right? Plus, next one is cosine x sine hyperbolic. We have sine hyperbolic square minus, we have a formula, right? So this is this is minus 1. And this becomes cosine square x minus 1 is minus sine square x. And cosine x sine hyperbolic y is common, right? This cosine x sine hyperbolic y, cosine x sine hyperbolic y is common. So we can actually simplify it a little bit. Cosine square x plus sine hyperbolic square y square minus cosine x sine hyperbolic y. This is sine square x right? Plus 1. We have to make sure that I didn't make any mistake. So I combine with one of this. So cosine x sine hyperbolic. Something is strange. I cannot combine these things together, right? So I made a mistake. So, sorry, we have to delete this part. So you can see that you can make a mistake very easily. That's nice. So let's try it again. So actually you can only cosine cube x let's try it again. Cosine x sine hyperbolic y. So we have a cosine square x minus cosine hyperbolic square y. Now I think we're in a better position. And cosine x sine hyperbolic y sine hyperbolic square y minus cosine hyperbolic square y, right? So it's not 1, but this part. And this becomes minus 1, right? So cosine square x plus sine hyperbolic square y square cosine x sine hyperbolic square y cosine square x minus cosine hyperbolic square y minus 1. So that's minus sign. Minus over cosine square x plus sine square y square cosine x sine hyperbolic square y sine square x plus cosine square y. This is correct, right? Right. And 1 to go. Maybe you should take a deep breath if I move on. Formula again before I move. Cosine x sine hyperbolic sine square x cosine hyperbolic square y. So sine square cosine hyperbolic square y. Minus. So 3 cosine square x plus sine hyperbolic square y sine x sine hyperbolic y. Let's check. So partial x 3. Same. So cosine x sine hyperbolic y cosine square x plus sine hyperbolic square y plus sine x sine hyperbolic y. You square it, right? Cosine square x plus sine hyperbolic square y square is minus 2 cosine x, right? And minus sine x. Cosine square x plus sine hyperbolic square y square. We have cosine cube x sine hyperbolic y plus cosine x sine hyperbolic square cube y plus twice over sine square x cosine x sine hyperbolic y. So 1, 1. Cosine square x plus sine hyperbolic square y square. So we divide equally cosine x sine hyperbolic y. We have cosine square x plus sine square x, right? Plus cosine x sine hyperbolic square y sine square y plus sine square x. First one. So the first one is cosine x sine hyperbolic y. So this is so cosine x sine hyperbolic y plus 1 plus sine square x plus sine hyperbolic y. Looks different. The previous one was let me see. So cosine hyperbolic square y minus sine hyperbolic square y is equal to 1. So this is actually cosine hyperbolic square y minus 1, right? So we have finally cosine square x plus sine hyperbolic square y square cosine x sine hyperbolic y sine square x plus cosine hyperbolic square y, which is minus. So Fz is sequent Z satisfies the CR condition. What about the derivative? So the cosine x sine hyperbolic y sine square x cosa saco. dz df is partial x partial u partial x partial v. So what is partial x partial u? And I forgot. Sorry. So this, I can move this. Sine x can I move this? No. Can I just throw it away? How can I move this up? Okay. Edit. Delete. It doesn't work out. How should I orange edit? Edit. Paste. Cut. Delete. It doesn't. So can I delete this? Thank God. And plus I y, and you go back to previous page. Cosine x, sine hyperbolic y, sine square x, y. And actually it will be 1 plus tangent square z. And I like you to feel this as homework. Okay. So I will give you homework. Check FC, CSC. One more. Tangent z. This will be real nightmare. So it may take me, I don't know how long, but for some time. So how about stopping today here and continue? Oh, next week we don't have a class, right? So after one more week. So you have enough homework for long weekend and next week too. So